Hello everyone and welcome back. Today we're going to be discussing a very important method of re-representing matrices, which is referred to as Gauss-Jordan Elimination. So let's just get off with a couple of basics that we definitely need to understand. So let us assume we have a matrix A, and let's assume that this is a square matrix. So same number of rows, same number of columns, and let's consider the system given by the following equation. AX is equal to B. So A is a matrix. That means X must also be a matrix and B also be a matrix as well. In particular, let's assume that X has the following form. X1, X2, down to say Xm. Let's assume that B also is a column vector of the form B1, B2, also down to Bm. So you should be able to test to see that these dimensions, when you multiply them, actually do line up. So let's first off start off with what is referred to as Gaussian elimination. So Gaussian elimination will turn the equation AX is equal to B into a different form, in particular UX is equal to C, where U is an upper triangular matrix. So if U is an upper triangular matrix, usually that last row in that systems of equation, usually we can solve just via, say, division, and then we can use what we call back substitution to find the rest of the variables in a bottom to top manner. So let's look at a very basic 2x2 system to sort of illustrate how Gaussian elimination works. So let's consider 3x minus 4y is equal to 5, and 2x plus 5y is equal to minus 1. So our goal is to make this equal to 0 such that we have an upper triangular system on the coefficients side of this. So if we write this in matrix form, what will we have? So that's going to give us 3 minus 4, 2, 5 times the solution vector xy is equal to 5 minus 1. So our goal is to perform some different types of operations in order to make this equal to 0. So let's just write that out. So our goal is to transform this into something 0 something times xy is equal to something while preserving that solution xy. So what I want to do is I'm going to focus on these coefficients 3 and 2. So if that was 3 and 3, 3 minus 3 would be 0 and I could eliminate one of them. But 3 and 2 are not the same number, so I need to transform these into the same exact coefficient. So what I can do is I can do 2 times row 1 minus 3 times row 2. And what I'm going to do is I'm going to define that to be our new row 2. So let's actually look at these particular results when we actually multiply row 1 by 2 and row 1 by 3, and then let's look at that result once we subtract. So if we multiply the first row by 2, that's going to give us 6 minus 8. This is not going to change. And then 2 times 5 is going to be 10. And then 3 times 2 is going to be 6, 3 times 5 is 15, and 3 times minus 1 is going to be minus 3. And now what we're going to do is we're going to do 2 row 1 minus 3 row 2 to give us our new row 2. So we're going to keep our first row the same as it used to be, in particular this particular row. So once we do that, what will we get? So 6 minus 6 is going to give us 0. Negative 8 minus 15 is going to be equal to minus 23. Xy is going to be equal to 10 minus negative 3, that's going to be equal to 13, and we're going to make our original row the same. So I'm just going to write it as 3 minus 4, 5. So the row that existed before I multiplied that by 2. And notice what I have done, I've made my coefficient matrix an upper triangular matrix. Therefore, you should easily be able to solve that last equation by dividing both sides of this equation by negative 23. So that last equation can be written in equation form as negative 23y is equal to 13 divided by negative 23 gives us y is equal to 13 divided by negative 23. And that's the first part of our solution. And then we can use back substitution, for example, to find the rest of that. Now, although back substitution may give you the correct solution as long as you're careful, some people will try to avoid back substitution because it's likely to involve complex arithmetic with fractions, especially if your system that you're working with is highly dimensional, for example, a 4 by 4 or even higher, where it's motivated to, for example, use software to solve that particular system. So if we were to use back substitution, how would that sort of follow? So since we have y, we can look at this first equation, which is going to be given by 3x minus 4y is equal to 5. Since we have y now, we need to solve this equation for x. So if we solve this equation implicitly for x, that's going to give us x is equal to 4y plus 5 all divided by 3. Now that we have the value of y, we can substitute that value of y here. So x is going to be equal to 4 times y, and we found y to be equal to negative 13 over 23. And then plus 5 all divided by 3, and that will give you the solution once you actually work out that complex fraction. Yes, it does give you the answer, but sometimes it can be a little bit more complicated than it actually needs to be. So one may ask, well, is there a nicer way to sort of solve systems of equations, even for the 2 by 2 or even higher? And the answer is yes. So the more sophisticated version of elimination is known as Gauss-Jordan Elimination. And Gauss-Jordan elimination actually takes one of two forms. So the first form, again, starts with Gauss-Jordan elimination. So first transform this into an upper triangular system. And one form of Gauss-Jordan elimination converts this into a diagonal system, say dx is equal to lowercase d, or some people will just directly convert this into an identity matrix, x is equal to e. Either one of these is perfectly fine. In order to get from diagonal to identity, you just divide by the diagonal entries, provided they are not zero, and that gives you your particular solution, x is equal to e. So let's look at a particular example on how we can perform Gauss-Jordan elimination, and let's actually use the same exact matrix example that we had before. So remember that we started with the system 3 minus 4, 2, 5 times xy is equal to 5 minus 1, and via Gaussian elimination this converted into 3 minus 4, 0 minus 23 times xy is equal to 10/13. Now our goal is to make this into an identity matrix on the left-hand side. So the first thing that we can do is actually get rid of these negative signs on the left-hand side, so we can actually multiply both sides of this second equation by -1. And that's going to give us 3 minus 4, 0, positive 23 times xy, and that's going to give us 10 minus 13 in that right-hand column. Now what I want to do is I want to eliminate this term and make it equal to 0. So I'm aiming for a diagonal matrix on the left-hand side. So what I can do is I can do 23 times row 1 plus 4 times row 2, and that's going to generate me a new row 1. That means I'm going to keep my last row the same. So let's actually go through those processes. So 23 times 3 plus 4 times 0 is going to give me a number. 23 times minus 4 plus 4 times 23 is going to give me a number. And then lastly, 23 times 10 plus 4 times minus 13 is going to give me a number. So 20 times 3 plus 4 times 0, that's just going to give us 69. 23 times minus 4 plus 4 times 23 is going to give us 0. But keep in mind, this is equal to 0 by design because we're focusing on that particular term in order to make that 0. So if that's not equal to 0, then you've done something wrong. And then lastly, we have 23 times 10 plus 4 times minus 13, and that's going to come out to 178. So that is going to be our new row 1. So that means our new system turns into 69,0,023 times xy is equal to 178 and minus 13. Now that we have a diagonal system, we can divide by the diagonal entries, right? So right now we're in dx is equal to d form. Now we're going to form it into ix is equal to e form by dividing by the diagonal entries. And that's going to give us 1001 times xy, which keep in mind is just xy, and that's going to be equal to 178 divided by 69, and then negative 13 divided by 23, and that is going to be the solution to the original system via Gauss-Jordan elimination. One of the important concepts that Gaussian and Gauss-Jordan elimination rely on is the following principle. In particular, scalar multiplication, addition of rows, and row swaps all preserve the solutions to linear systems. When we multiply an equation by, say, 3, when we swap, say, rows 1 and 3, or when we add, say, rows 2 and 4. Even though we are now working with different systems, the solution to that system will always be the same. We're not going to prove it here, but definitely if you're in a theoretical interest for linear algebra, I highly recommend trying to prove this, say starting with a 2 by 2 system and working up to, say, an n by n system, because this is a very, very important principle. With these things in mind, let us work through a nice 3 by 3 example just to make sure we have everything understood. So the 3 by 3 matrix equation that I'm going to be focused on now is going to be 3 minus 2, 5, 4 minus 7 minus 1, 5 minus 6, 4. And the variables we're going to be working with are going to be x, y, and z. And let's assume that those three equations are equal to 2, 19, and 13. So, for Gauss-Jordan elimination to work, our first focus is to make these entries equal to 0. Once we make those equal to 0, the second phase is going to be making that equal to 0. That's going to give us an upper triangular system. Then we're going to transform this into a diagonal system. So our next goal is to make those two equal to 0. And lastly, make that equal to 0. That's going to give us a diagonal, or moreover, an identity system, which is going to give us the solution to the system, provided that the determinant of the coefficient matrix is non-zero. So some of the quickest ways you can sort of figure out what numbers you need to introduce to the equation is look at the least common multiple of the rows you're going to manipulate. One of those rows are going to be remain fixed and the other row is going to change. For example, we're not really going to be changing row 1, so our goal is to manipulate row 2 and 1 in order to eliminate row 2. So the least common multiple of 3 and 4 is 12, so you can ask yourself, how can I make both of those equal to 12? So what I can do is I can do 4 times row 1 minus 3 times row 2, and that's going to give me 12 minus 12, which is going to give me 0 in that position where that 4 is. So I'm going to define that to be my new row 2. And then I'm going to do the same for row 1 and row 3. So for example, I'm going to do 5 times row 1 minus 3 times row 3, and that's going to generate my new row 3. So what is that going to give me? So I'm not going to be changing my first row, so I'm still going to have 3 minus 2, 5 times x, y, z is equal to 2. Now that's going to be equal to 0 by design, and what am I going to have in the other rows? So I'm going to have 4 times minus 2 minus 3 times minus 7, that's going to come out to 13. 4 times 5 minus 3 times minus 1, that's going to give us 23. And then 4 times 2 minus 3 times 19, that's going to give us minus 49. And then we're going to do the same for row 3. So again, we're going to have 5 times 3 minus 3 times 5, that's going to give us 0 by design. And then we're going to have 5 times minus 2 minus 3 times minus 6, that's going to be equal to 8. And then 5 times 5 minus 3 times 4, that's going to be equal to 13. And lastly, 5 times 2 minus 3 times 13, that's going to give us minus 29. So that's our first phase of this procedure. And now let us focus on the next entry, which is going to be that 8. So now I'm going to be using row 2 and row 3 by focusing on this 13, which is going to remain fixed, and we're going to be focusing on that 8. So the least common multiple of 8 and 13 would be, again, the product of the two. So what am I going to do? I'm going to do 8 times row 2 minus 13 times row 3, and I'm going to be defining that to be our new row 3. So rows 1 and 2 are going to remain fixed. I'm going to have 3 minus 2, 5, 0, 13, 23. And what I'm going to do is I'm actually going to write this system in a different way. I'm going to write it in this way. Some people call this the augmented form of the matrix equation. That is, everything to the right is going to be our column vector, or our b in linear form, and our x, y, z variables are going to be implicitly written here. So that's going to stay 0. This is going to be equal to 0 by design. So what is that last value going to be? So that's going to be equal to 8 times 5, well, not 8 times 5, but 8 times 23 minus 13 times 13, and that's going to come out to 15. And then 8 times 2 minus 13 times negative 29, that's going to come out to minus 15. And that gives us our upper rectangular system. So now what I can do is I can make that entry equal to 1, so I start my Gauss-Jordan process. So I can do row 3 divided by positive 15, and that's going to give me our new row 3. And this is going to generate this system, so 3 minus 2, 5, 0, 13, 23, 0, 0, 1, augmented with 2, minus 49, and minus 1. Now that we have our upper triangular system, now our goal is to focus on these entries. So I'm going to be using row 3 and in addition to row 2 and row 1. So these are going to be the ones that are changing. Row 3 is going to be remaining fixed. So how am I going to do that? Well, what I can do is I can do, for example, row 2 minus 23 times row 3, and I'm going to call this my new row 2. And I'm going to do row 1 minus 5 row 3, and that's going to be our new row 1. So you may want to pause the video and sort of see what that is going to come out to. So the last row is going to remain fixed. And then we're going to have minus 3, 2, 0, minus 7, 0, minus 13, 0, and 26. Now notice we have something very, very nice. On that second row, I can divide everything by negative 13. That's going to make that left circle equal to 1, which is ideally what we want. So we're going to do row 2 divided by minus 13, and that's going to give us our new row 2. So that's going to give us minus 3, 2, 0, 0, 1, 0, 0, 0, 1, augmented with negative 7, minus 2, and minus 1. Now, our last thing is to focus on that entry, make that 0, and ideally make that 1 as soon as possible. So what I can do is I can do row 1 minus 2 times row 2 in order to define our new row 1. So once I do that, what am I going to get? So negative 3 minus 2 times 0, that's going to give us minus 3, 0, 0 by design. Negative 7 minus 2 times minus 2, that's going to be minus 7 plus 4, that's going to give us minus 3. And then we're going to have 0, 1, 0, minus 2, and then 0, 0, 1, minus 1. And then lastly, I can divide row 1 by minus 3, and then it's going to give us our new row 1. And once I do that, that's going to give us 1, 0, 0, 0, 1, 0, 0, 0, 1, augmented with, or I'm not going to write it augmented, I'm going to write it like so. So that's going to be equal to 1, minus 2, and minus 1. So since the identity matrix times our column vector is just going to be equal to the column vector, our solution is listed there. Therefore, our solution to the original system is x, y, z is equal to 1, minus 2, minus 1. All right, and that's Gauss-Jordan. So let's actually just do one more example just to make sure we got it. So for this example, notice that we are starting with a couple 0 entries here, which is definitely going to be a good thing. It's going to make us get to the final solution a little bit quicker. But the first thing I want to do is convert this into augmented matrix form so I don't keep on writing the same symbols over and over again. So in augmented form, this becomes 2, 1, 2, 4, 0, 3, 0, 5, 4, augmented with the right-hand side, 1, minus 5, and 13. So what is the first thing that I need to eliminate? Well, I need to eliminate that 4. So let's just go ahead and do that. So what I'm going to do is I'm going to do 2 times row 1 minus row 2, and that's going to give us our new row 2. Since I already have a 0 located in this bottom row, I'm not going to be manipulating row 3, at least not for now. So that's going to be the only thing I need to get for those first 2 zeros to be existent. So once I perform that, what will I get? So row 1 is going to remain fixed, so 2, 1, 2 augmented with 1. The last row also is going to remain unchanged, so 0, 5, 4 all the way up to 13. And then on the second row, I should come out to 2, 0, 1, and 7. So the next thing I need to focus on is that, and that's going to put it in upper triangular form. So I'm going to be using this 2 as what we call a pivot in order to eliminate that 5. The least common multiple of 2 and 5 is going to be 10. So what I can do is I can do 5 times row 2 minus 2 times row 3, and that's going to generate our new row 3. So I'm not going to be changing rows 1 and 2, so I'm just going to repeat them. 2, 1, 2 augmented with 1, 0, 2, 1 augmented with 7, 0, and 0 by design. And the last number is going to be what? So that's going to be 5 times 1 minus 2 times 4. So that's going to be 5 minus, what is that? 5 minus 8, that's going to be minus 3. And then we're going to have 5 times 7 minus 2 times 13. That's going to come out to 9. Now that we're in upper triangular form, I could either focus on these two, or I can make that last row 1. And they're nice multiples of each other, so I'm actually just going to go ahead and do that. So row 3 divided by minus 3, that's going to give us our new row 3. Once I do that, I'm going to have 2, 1, 2, 0, 2, 1, 0, 0, 1 by design, and then 1, 7, and finally minus 3. Our next focus is going to be that 1 and that 2, and we're going to be using this 1 in the bottom right hand corner in order to pivot around the other 2. So in order to do that, I'm going to be doing row 1 minus 2 row 3, and that's going to give me our new row 1. And for the other, that's actually going to be very easy, row 2 minus row 3, and that's going to give us our new row 2. Keep in mind that these operations are not unique. There are other alternatives that you could do. I'm just choosing the ones that at least seem the easier to work with, at least to me. So what is that going to give me? So we're going to be changing rows 1 and 2. So once you work through that, what will you get? That's going to give us 2, 1, 0 augmented with 7, 0, 2, 0 augmented with 10, 0, 0, 1 minus 3 since the last is not going to change, and that gives us that. So the next thing I want to focus on is going to be this 1. So how am I going to be changing that? So what I can do is I can do, let's see, we can do 2 times row 1 minus row 2 in order to get a new row 1. So once we do that, we're going to have 2, 0, 0, 0, 1, 0, 0, 0, 1, augmented with 2, 5, minus 3, and then I'm going to just divide row 1 by 2 in order to generate a new row 1. Once I perform that transformation, I'm going to have the identity 1, 0, 0, 0, 1, 0, 0, 0, 1, augmented with 1, 5, minus 3. That means my solution, x, y, z, to the original system is going to be 1, 5, minus 3. And that is how you do Gauss-Jordan elimination. Of course, you can do this for a 4x4, 5x5, or even higher, and it doesn't actually have to be a square matrix either. You can have a 15x18 augmented system, and you can still use Gauss-Jordan elimination, but a couple weird things may come up in the non-square cases for systems, but we'll talk about that later. But definitely, if you do not already have Gauss-Jordan elimination down pat, I definitely recommend doing so because Gauss-Jordan elimination has several applications that we're going to introduce in the future, in particular inverses of matrices and reduced row echelon forms of matrices. But until then, I hope you take care. Thank you.